Kevlar and outer layers of fiberglass with the final black fiberglass layer on the outside for aesthetics.
So with the material properties known, we can go into the finite element software to determine the stresses and forces throughout the hull. And for this, we chose the spring configuration due to the high accelerations and the concentrated resistance forces. So each component within the hull, such as the driver, batteries, motors, were modeled as a lumped mass, which connected to the hull through two support frames to help distribute the load. We then applied a longitudinal acceleration force, or acceleration, and we also modeled a submerged pontoon going at top speeds. And while this should not happen in real life, it represents an emergency situation that we'd like to design for so it does not fail in such a case. So looking at our stress results, we see a maximum stress of 1260 psi, which occurs from a reaction force from the pontoon frame. And just a reminder, the fiberglass aramid composite had a yield strength of 8310 psi, which gives us a factor of safety of 6.6. We also analyzed the pontoon frame. Here we have to design for high loads, but we really want to minimize the weight. So our first design solution involved an aluminum tube, which worked very well. It gave us a high factor of safety with a low weight. But then we looked at the alternative of steel, where we use a box beam and with a rectangular cross section in the members that were most critically stressed. Here we had about a 10-pound increase in weight and a slightly lower factor of safety, but we determined that aluminum manufacturing was out of our reach, so the cost savings of manufacturing the steel frame ourselves was more important than the weight savings of going with aluminum.
So since we decided to go with a steel frame, the team was actually able to weld the frame ourselves with help from an experienced welder. And the frame connects to the pontoons via pin connections. And the pontoons, as you can see in figure 2 over there, have PVC through the middle, and that PVC is fiberglassed in, so it's secure to the foam. To construct the pontoons, they're made out of styrofoam, and we wire cut 3 cuts to create the basic shape, and then hand sanded them down to create the complex contours. For the layup, we used a fiberglass and Kevlar layup, and then vacuum bagged the entire pontoon, and you can see the finished product in figure 3. So for construction, construction overall took us about a month to complete. We first printed out cross-sectional areas of the hull at 1-foot intervals along the hull and attached these to a strong form called strong back. In between the stations, we attached these strips you can see in figure 1 called stringers, and they interpolate the shape of the hull from station to station. Once that was done, we attached a polyester peel-ply fabric so that when we were epoxying our layers of fiberglass, they would not stick to the wood. We laid our first half of the composite layers, starting with fiberglass, 2 layers of Kevlar, a layer of fiberglass, and then moved on to the foam core. And after that dried, we did the last 4 layers. And when that was done, we were able to remove the hull from the form, as you can see in figure 6. Construction safety was a large concern of ours. We worked with Northeastern closely to ensure that we were safe while building the boat. As you can see, we had personal protective equipment, and Northeastern built us a temporary ventilation system in the basement of Richards Hall. Our total budget cost was around $6,000, and the team applied for and received a $5,000 provost grant from the university to help offset costs. Overall, you can see that our design passes the designed goals that we set for ourselves and is expected to exceed the performance of the 2011 hull. Thank you for your time, and if you have any questions, please ask me that. Yes?
One of the things I had was the sort of front to back position of those outriggers. Does that have any implications, or do you just guys sort of take the back and front to back?
When we ran the modeling software, we played around with that. Ideally, we wouldn't want to shift it too much, like from event to event, just for ease of transition from sprint to configuration to endurance configuration like that. So we settled on an optimal location and focused more on the position of heavier objects in the boat, like the motors and the driver, to augment the center of gravity and plug the water plant.
The location of the pontoons longitudinally as well as vertically was played with through the analysis. We just continually run it, change it a little bit, see how the results came out. Okay. So they were optimized.
Any thoughts into what the surface finish effect had on the boat?
Yes, we finished our construction with 2 or 3 layers of epoxy smooth coat and sanded between each layer to get out any imperfections. So there is a smooth layer on the outer surface of the boat.
I guess that plays a large factor.
Yeah, as Brent mentioned, there's a surface drag coefficient, how much the boat is slowed down by that friction, so we tried to minimize that.
And there's lots of people who have built fiberglass boats, obviously, so I mean, it's a well-explored area that the finishing epoxy coats are a good way to reduce that.
Yeah, the fiberglass strength, you quote, seemed kind of low to me. I'm not an expert, but was it low? And if so, do you know why?
Yes, from testing, we figured that our samples that we made were not ideal because of our construction method, that it was human error, but I think that's what that better.
Yeah, I mean, the values were for the entire composite sandwich, not just the fiberglass alone, but I mean, we did do the layup on the main hull without vacuum backing as compared with pontoon.
Well,
and I think-
excuse me, I thought I saw things that said fiberglass strength, AKSI, something like that.
That refers to the whole like sandwich composite, including the foam core, which kind of skews our results down as that increases our area. Which
Does that mean it's not really the fiberglass strength?
Not the fiberglass alone.
it's our entire material sandwich.
Okay,
It was only referred to as fiberglass because it was in opposition to the carbon fiber version of the same layout.
thank you.
Yes.
The rear of the boat with the flat, blunt configuration just strikes me as not optimum for drag. Eddy currents and all that. Did you think about that? Why is it that way?
I mean, it's definitely considered when we were doing the design, and if it was strictly a displacement hull, that would have been ideal. And we had also played with the idea of maybe having a removable section that would taper that to a nice, almost like a sailboat tail end, where you get just great transitional lines off the back. But given the Sprint, a tail like that really wants to suck you down into the water, so it kind of hurts your planing efficiency. So we did try and minimize it, as I said earlier, but we settled on the final design of a small but still flat back for that purpose.
Additionally, in the endurance, the stern is somewhat lifted from the water, so that doesn't play as much of a role because of the trim configuration.
The pontoon assembly seems to be like the weakest, relatively speaking. What would you gain if you could find like
The pontoon itself, or the frame, the whole thing?
The
So,
frame.
I mean, as Andy talked about a little bit, we could have lost about 10 pounds of weight moving to an aluminum construction, but it would have been about $1,200 for TIG welding manufacturing, and so we decided that the 10 pounds was probably worth it. There's also the idea of the factor of safety that was considered, but the evaluation proved that this steel would be sufficient for our needs.
You mentioned a 3-point bending test for your material. Did you consider it might have anisotropic material properties because of lamination?
Yes, the way we decided to lay up the sandwich, as the fibers are biaxial, we would alternate between the 0 and 90 configuration and the 45 minus 45 configuration. So we said the material was quasi-isotropic, and then our high factor of safety kind of allows this to be a good approximation.
And in the end, it will mostly be bending on the structure.
There was a point during the testing where you could see, I mean, there's a clear elastic point on the curve, but then later on, as you just was watching it, you could see that the foam core started to failure, and then it ceased to be bending at that point. It was really just structural delamination.
Did you model any designs that did have dead rise at the transom at any degrees, and if so, what were the results?
There is a component of the Orca software that allows you to rapidly generate a generic hull form in various configurations, like more deep V or more planing and things like that. So that was kind of where we started off, just as a ballpark. So I think we ended up maybe 6 generic forms like that as a very preliminary analysis, quick kind of plug and chug, and then took the advantageous parts of each.
Since the hull is narrower, narrower compared to the first boat design, will it affect how many solar panels you get on? How will it affect your power?
If you see in this picture here, actually, the way the panels are laid out is significantly different than the previous year's boat, with 9 panels on the front and 3 in the back, and that was again to help move the center of gravity forward. It will take some different rigging for sure, and some careful management will definitely be paid to mounting.
Okay, they're downstairs if you want to question the man more, but thank you.
Where's Katie?
I guess I can let you guys do welding team.
Welding team.
No, I left it on the chair. I was gonna put it on the table. I was like, but if it goes off, it's gonna buzz.
Yeah, yeah.
Which one do we look at?